So today we shall talk about radius of curvature of a curve at some point P. Radius of curvature of a curve at some point P on the curve. And most of the times we have a very big formula for this radius of curvature. We want to memorize that formula for exam purpose or like that. But the main thing is that if you know the concept lying behind this radius of curvature of a curve, then you don't need to memorize that big formula for radius of curvature. You can easily derive that formula in 2 to 3 minutes. So let us see what is the major concept behind this radius of curvature of a curve at a point. So suppose we have a curve like this, y equal to fx, and at some point P on this curve, we want to measure the radius of curvature of this curve. So essentially what that means, what radius, so whenever we talk about radius, it seems that there is a term of circle is involved there. So actually there is a circle is involved here. So radius of curvature is nothing but the fact that at the point P we consider the circle approximation. Circle approximation to the curve y equal to fx. So this is nothing but the fact, this radius of curvature is related to the fact of, just remember this, circle approximation to the curve at the point curve y equal to fx at the point P. Okay, so let us try to just see what is this. So suppose in this picture this is a curve y equal to fx and there is a point P here. So at this point we want to consider a circle at this point. So a circle, not at this point, we want to consider a circle with center x0 y0 and with radius r, which can approximate this curve in a very small neighborhood of this point P. That means if you take a very small neighborhood around this point P, in that small neighborhood, the circle, the portion of the circle and portion of the curve will look very much similar, and there will be no difference between the portion of the curve and portion of the circle. That means two curves, that is the curve of the circle around that point and the curve of the original y equal to fx will look similar. So when that will happen? That will happen if, so suppose the equation of the circle is some fxy equal to 0. So if you take we consider that the circle, so it is differentiable, it is a differentiable curve, and also this y equal to fx is a differentiable curve. So if you consider the derivatives up to second order, that is dy dx and d2y dx2, those should be same though at this point. That means why I am saying that. So if you consider the curve y equal to fx, you can just approximate this curve by Taylor series approximation, where dy dx, d2y dx2, these terms will be involved. Okay, and if you take the equation of the circle and approximate this equation of the circle around this point P in Taylor series expansion, then also there will be terms like dy dx, d2y dx2. So if we say that these two curves at the point P, around the point P, are same, then the derivatives dy dx, d2y dx2, which are the major terms related to the Taylor series approximation, the first derivative, second derivative, etc., should be same at the point P for both the curve y equal to fx and the circle fxy equal to 0. Okay, so this is the essential concept. So what is the concept? Concept is at this point P, for both the circle and this curve, the first derivative and the second derivative at least will be the same. Okay, first derivative same means it's simple. The geometric thing is the tangent will be same, but also the second derivative must be same, and that we will take that into count to get the radius. Okay. So this is the essential concept. So what is the essential concept? Essential concept is that whenever we are talking about radius of curvature of a curve at a point, we are considering a circle approximation of the curve around that point. That is, we are considering a circle with center x0 y0 and radius r, which exactly matches with the curve around that point P. And the inner meaning is that the first derivative and second derivative and so on will be same for the circle and the curve at that point. Okay, so I hope that this is clear. Now we shall talk about the formula for this radius r. So we need to know this radius r now. So what is the radius r? That we need to know. Okay, so let us derive the formula for the radius r. So suppose the circle approximation we have used, and that circle has center at x0 y0 and radius r. Then what is the equation of that circle? Equation of that circle will be x minus x0 whole square plus y minus y0 whole square equal to r square. Now you can simply ask a question that here I don't know what is x0 y0 is, I don't know what is the radius r is, then how we can get the radius r? The essential fact is that here if you look at the picture here that I previously drawn, so there is a curve y equal to fx and there is a circle, so there is the radius r and it is x0 y0 is the center. So you don't know what is r, you don't know what is x0, what is y0, but you know, since you know the equation of this curve y equal to fx and you know the point P, you know what is the value of dy dx at P and d2y dx2 at the point P. These two things you know, because you know the equation of the curve is y equal to fx and you know the point P also. So you can from that you can figure out dy dx at P and d2y dx2 at P. So you have that information, and we will use this information to get the radius r, and that is very simple. Let us check. So suppose this is the equation of the circle, that is denoted by equation number 1. Then simply take derivative with respect to x of this equation on both sides. Then you will get 2 into x minus x0 plus 2 into y minus y0 into dy dx equal to 0. Since r is a constant, derivative will be 0. So if we simplify this equation, it will be x minus x0 plus y minus y0 into y dashed equal to 0. So this is your equation number 2, where y dashed is meant for dy dx. Okay, so you have your equation number 1, equation number 2. Now you again take the derivative of this equation number 2 with respect to x, then see what you will get. So if you take the derivative of this portion with respect to x, you will get 1, and for this portion you will get simply dy dx into y dashed plus y minus y0 into ddx of y dashed. Okay, so that means ddx of dy dx, that is d2y dx2. So this is d2y dx2. Okay, so if we write this, we will get, so again this is dy dx, so 1 plus dy dx whole square plus y minus y0 into d2y dx2 equal to 0. That means 1 plus y dashed, sorry, this is y dashed, 1 plus y dashed whole square plus y minus y0 into y double dashed equal to 0, where, so this is my equation number 3, where y dashed stands for ddx, means dy dx, and y double dashed stands for d2y dx2. That is standard. Okay, Now from this equation number 3, you will get y minus y naught is equal to, so this is very easy to get, is equal to minus of this. Okay. So suppose this is your equation number 4. And if you substitute this expression for y minus y naught from this equation number 4 into the equation number 2, then you will get simply x minus x naught equal to 1 plus y dashed square by y double dashed into y dashed. Okay, because from here you can see just x minus x naught equal to minus of y minus y naught into y dashed. So in place of y minus y naught, you can just substitute this expression given by 4 and that will give you this. So suppose this is your equation number 5. Now what we will do, we will simply substitute the expression for y minus y naught and x minus x naught into equation number 1, that is the equation of the circle, this. Okay, so and let us see what we can get from there. Okay, so if we substitute, so let us take a fresh page for that. So essentially, what is the equation of the circle? Equation of the circle is this. Y minus y naught is this, and x minus x naught is this. Now, sorry, x minus x naught is this, plus sign will be there. Now, if we replace y minus y naught here and x minus x naught here, then we will get 1 plus y dashed square by y double dashed. So, the whole square of this thing into y dashed square plus y minus y naught, for we will get 1 plus y dashed square by y double dashed whole square. So this equal to r square, and from there we get r square equal to, if we take this 1 plus y dashed square by y double dashed whole square term common, then so if we take this common, then we will get 1 plus y dashed square here. And so you can just now see that in the numerator there is a term. So let us just try to figure out what this is. So in the numerator we have a term like this into 1 plus this, and in the denominator you have y double dashed whole square. Okay, so now if you take this multiplication, that will be simply 1 plus y dashed square cube, so whole cube of 1 plus y dashed square, because here is a 1 plus y dashed square and here is a whole square of 1 plus y dashed square, and in the denominator it is simply y double dashed whole square. So this is the expression for r square. Now you take the root of this, so r is simply 1 plus y dashed square to the power 3 by 2, and this is y double dashed. So this is the expression for the r, that is simply in terms of dy dx 1 plus dy dx whole square to the power 3 by 2, and in the denominator it is d2y dx2. Okay, so now you see that you got the formula for the radius of curvature, which are usually in students want to memorize this formula. But you can easily derive this formula from one thing that you have to remember, that radius of curvature is nothing but a circle approximation at that point. Okay, so this is the formula for radius of curvature. Now here in many text here mod sign is given here, because this, the simple reason is that the radius cannot be negative, but you can consider this mod sign, and without that you can also consider, because you have to take the positive value of d2y dx2 at that point. That's why. So this is nothing special. So essential thing is that this is the formula for the radius of curvature, and you can derive this formula within a few minutes if you know what is the concept lying behind this radius of curvature. That is a circle approximation. Again, I am saying that is the circle approximation of the curve at some point. Okay, and this is the radius of that circle. Now you see that in this formula we know what is y dashed, we know what is dy dx at the point P, we know what is d2y dx2 at the point P, because we know the equation of the curve y equal to fx. So we can just replace here d2y dx2 and dy dx, the value of this, and we can get this r for at this point. We can get the radius of that circle at that point. And that is the radius of curvature. So this is the radius of curvature. That is the radius of the circle. Okay. And now sometimes the equation of the curve, instead of y equal to fx, it can be given in form of x equal to fy. In that case, instead of taking derivative with respect to x, you have to take derivative with respect to y. And simply this dy dx will be replaced by dx dy, and d2y dx2 will be replaced by d2x dy2. And that is the alternative formula for curve equation of where the equation of the curve is given by x equal to fy type. Okay, so there is nothing special in that. So simply this is the formula for the radius of curvature. And now let us come to the point, what is curvature, that we all know by mathematical figure. The curvature of a curve, if we call it k at some point P, is 1 by radius of curvature. So where r is the radius of curvature at P of that curve, of the curve. So if r is the radius of curvature of the curve at P, then simply the curvature is the reciprocal of that radius, that is 1 by r is the curvature. It is called the curvature of curve at P. So what does that curvature means? Actually this means that the rate of turn, this is the rate of turn of the curve at P. So this is the measurement. The curvature is simply the measurement of the rate of turn of the curve at P, which is simply 1 by r, where r is the radius of curvature of the curve. And this radius of curvature, you can simply get it from the circle approximation. So, and one thing you can notice, that if your radius is big, then the curvature, that is the rate of turn, is small. And if your radius is small, then the rate of turn is higher. So we can just simply check it. You take a circle with a big radius, and at the same time you take a circle with a small radius, So now you see what is the difference. Suppose this is a point P. If you take for the circle with big radius, suppose you take this portion around this point P. So around this point, the turn, how the tangent turns. So if you measure the turn of the tangent from this point to this point, the difference will be much smaller. And within this range, if you consider for this circle, if you consider the turn for the tangents, total turn for this circle, which has a small radius, the total turn angle of turn of the tangents for this small circle will be much higher than this big circle. Therefore, if your radius is small, then the curvature is higher, and if your radius is higher, then curvature is small. And you can just feel it from the curve perspective also. Suppose there is a sharp curve which has a sharp turn in this point, at this point P, then you can approximate this with a circle which has a very small radius. But on the other hand, if there is a curve which has not a sharp turn, then to approximate this with a circle, you need a circle of big radius. So this is the difference. So if you have a small radius, the turn is higher. If you have a big radius, the turn is lower. That's why the curvature is the reciprocal of 1 by r. So major thing, so remember the major thing behind the whole learning is the one line that radius of curvature is only related to the circle approximation. Circle approximation of the curve at the point P. So this is the major thing. You remember this circle approximation. So at some point of the curve, we are approximating that curve by a circle. That is the main thing, major thing you need to remember. And from that, you can easily derive what is the formula for radius of curvature.